Hello, we have here a long straight wire. Currently there's no current in it. So where are all these little compasses pointing? They're all pointing northward, right? They're pointing in the direction of the Earth's magnetic field. When we pass the currents through this long straight wire, those little compasses will now form a concentric circle. What does that tell us? It's telling us that this current, electric current, has produced a magnetic field. And the magnetism kind of flows in a concentric circle. So this magnetic flow is called magnetic flux. And the strength of a magnetic field is described by this quantity called magnetic flux density, usually denoted by the symbol B. And for the magnetic field produced by a long straight wire, the magnetic flux density is given by this formula. Mu naught I divided by 2 pi r. Mu naught is the magnetic permeability of free space. For now, you just take it as a constant. I is the current, which makes sense. The stronger the current, the stronger the magnetic field. The denominator is the most interesting. It shows 2 pi r. So r is measured from the center of the wire. So 2 pi r kind of makes sense because we are looking at concentric circles, right? Which have a circumference of 2 pi r. If we were to represent the magnetic field using a field pattern, it will look like this, those red concentric circles here. Now, if you were asked to draw this in exams, make sure you draw the spacing becoming larger and larger. This is to show that you're aware that the magnetic flux density decreases with r. So the further away, the weaker the magnetic flux density. As for the direction, you can use the right hand grip rule. So make sure your thumb point in the direction of the current. Your fingers will provide the direction of the magnetic field. So see, your fingers are pointing like this, right? So the magnetic field is going like that too. So if the current is going downward instead, then you got to point your thumb down, right? The thumb points in the direction of the current, and now your fingers are pointing this way, and therefore the magnetic field is also this way. If you see the cross like this, it means that there's a current going into the screen. It's like you're looking at the back end of an arrow, right? And then you see a cross. So there's a current going into the screen. In that case, you point your thumb into the screen. Now your fingers are pointing this way, so the magnetic field is also in the clockwise direction. If you see this symbol, a dot, that means there's a current coming out of the screen. It's like you're looking at the tip of an arrow. In this case, you will point your thumb towards you. Now your fingers are curling this way, right? So the magnetic field is also going in the anti-clockwise direction. Okay, the magnetic field produced by a long straight wire is actually rather weak. So is there any way I can get a stronger field? Now maybe I can bend the wire into a coil instead. Yeah, so instead of a long straight wire, I bend it and then let it join itself. So every section of this coil will be producing a magnetic field that looks somewhat like that. So at the other end, the magnetic field will be this way, right? Because the current comes out here and enters the screen here. Can you use your imagination to imagine what the resultant field look like? If your imagination works well, you should see something like this. The nice thing about the coil is the magnetic field inside the coil is stronger than the magnetic field outside the coil. Kind of makes sense, because inside the coil, every section of the coil is producing a magnetic field that is upward. So they kind of reinforce one another. But outside, the magnetic field produced by this section will be downward, but the magnetic field produced by this section will be upward. So outside the coil, some of the field is actually cancelled out. If you want to know the direction of the magnetic field, you can use the right hand grip rule again. But this time, the fingers correspond to the direction of the current, whereas the thumb correspond to the direction of the B field inside the coil. So the rows of the fingers and the thumb have swapped, yeah? See, remember last time? The thumb was the current and the fingers are the B field. But now the thumb is the B field and the fingers are the current. The formula for the magnetic flux density is mu naught I divided by 2r. And this corresponds to the magnetic flux density only to the position right at the middle, right at the center of the coil. From the spacing of the field lines, you can tell that the magnetic flux density is not uniform everywhere inside the coil. The magnetic flux density at the center is actually weaker compared to the regions nearer to the wire. Okay, so if the current is going the other way, then you just got to wrap your fingers in the same direction as the current. Then the thumb will be telling you that the magnetic field inside the coil is pointing downward. Now the magnetic field produced by a flat circular coil is still not very strong. How can I get an even stronger magnetic field? We can put many coils together. Can you imagine? Coil. You get a long solenoid, right? Can you imagine what the resultant magnetic field will look like? Something like this. You can still use the right hand grip rule. Just like for the coil, the thumb corresponds to the direction of the magnetic field, and the fingers correspond to the direction of the current in each coil. Now you know why we are born with thumbs and fingers, right? It's so that we can study magnetism. Now the magnetic field produced by a long solenoid resembles that produced by a bar magnet. So we also talk about the solenoid having a north pole and a south pole. So the north pole is where the magnetic flux gushes out from the solenoid, and the south pole is where the magnetic flux gushes back into the solenoid. Now, do you notice that the magnetic field lines are drawn equally spaced out inside the solenoid? That's right. The magnetic field inside a solenoid is actually uniform. So this uniform magnetic flux density has the formula B is equal to mu naught Ni. Who is this small n? It's not the number of turns, It's actually the number of turns per unit length. It's like you count the number of turns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this one will be 14 divided by this distance, the length of the solenoid. Notice also that the magnetic field outside the solenoid is much weaker. Also, the magnetic flux density at the ends of the solenoid is actually slightly weaker. You can see the field lines starting to diverge. In fact, just by some simple logic, you can deduce that the magnetic flux density here exactly half the magnetic flux density everywhere inside the solenoid. Here and here is half-wise inside the solenoid. But for the A level, we always assume that the magnetic field is uniform everywhere inside the solenoid and zero everywhere outside. Doesn't this remind you of the parallel plates for electric field? Alright, that's all. Ta-ta!